Okay, now we're going to be solving rational inequalities. And we're going to use the exact same method for rational inequalities that we did for polynomial inequalities. We're going to find the zeros and all that. We're going to test intervals, same. It's going to look very similar. Given a rational function, a rational inequality has the general form, and we have the exact same general forms: less thans, greater thans, less than or equal to's, not equal to's. The inequality f of x is greater than 0 is true when? And that's when f of x is positive. And again, I'm going to put that is true when you are above the x-axis. That's where f of x is positive. The inequality f of x is less than 0 is true when you're below the x-axis. So again, if they're asking us where is f of x greater than 0, they're simply saying where is your function above the x-axis. Let's look at this function, and it's graphed over here, and let's see if we can determine the intervals where our function is positive. So therefore, we can see up to, looks like this point right here, you have a function that is above the x-axis. And then at that point, it jumps down here below, and then it's below it everywhere till you hit to this point. And then from there over to this asymptote line, it looks like it's above it again. Then it jumps back to below it, and it's below it everywhere until it hits here, and then it's above it again, and it's above it from there forever. So that would look like this as an interval notation. That'd be everywhere from negative infinity up to whatever this asymptote line was, which is negative 1, 2, 3, negative 4. And since it's an asymptote line, here's what you got to be cautious of. It's not or equal to at that asymptote line because it cannot be included. We'll talk more about that later. And then we have an open, since it's greater than, that's going to be an open circle for all these. So let me change this one over here also to an open circle. So that's going to be everywhere from negative 1 to 1, 2. And then finally everywhere from 3, 4 to infinity. So that's where your function is above the x-axis. Where's your function below the x-axis? Well, it's below it from here over to here, because you can see it down here. It's below it from here over to here in that region, because you can see it down here. So that would be everywhere from negative 4 up to negative 1, or 2 to 4. That's where your function is below the x-axis. So again, notice that the rational function switches signs at both its zeros and its vertical asymptotes. There's not just one place. And in the last section, it might jump from above to below at just the zeros. But now, like in this case here, notice that it was above it, but at this asymptote line right here, it jumped from up here at the asymptote line to down here. And same thing at this one. It was up here, and then on the other side of the asymptote line, it was less than. So it was greater than, and then jumped to less than. And here's another place. It was less than, and then on the other side of that 0, it is now greater than. So your function can jump the x-axis at asymptote lines, at holes, or at zeros. So we've got to be cautious of all three of those. So remember those as we're going through these steps, and it's going to make more sense. We're going to move all terms to one side, just like we did on the last one. We're going to find the zeros of both the numerator and the denominator. Why? Because this is going to tell you all your x-intercepts, and this is going to tell you all your vertical asymptote lines, or your holes, because that's where it can jump from above to below, or vice versa. We're going to plot these points on the number line. Asymptote lines will always get open circles because they can't be included. Even if it's a greater than or equal to, your graph cannot be equal to an asymptote line. So always an open circle at an asymptote line. Choose test points in each interval, plug them in, test them, and then write the solution set. So everything else looks just the same. So step number 1, and I call these critical values. We're going to find all the zeros. So we're going to set the top equal to 0, and we're going to set the bottom equal to 0. So we're finding all the x-intercepts, and we're finding all the holes or asymptote lines. So your critical values are at negative 5. That's all your x-intercepts. And then the asymptote lines, the places on the bottom where x cannot equal because you get a 0 on the bottom, we're going to solve it as well. So at negative 5 and negative 2, that's our critical values. That's going to tell us where we're going to test. So let's plot those. Now let's choose some test numbers. We'll test maybe negative 6, negative 4, and 0. We're going to plug it into our original inequality, and we're going to see what happens. And here's what we get. When I plugged in -6, I got a true statement. And notice here, I'm just simply testing if it's greater than 0. So honestly, greater than 0 just means, is it positive? That's all I'm concerned with. This also gives me a true statement. So my answer is going to be the first region. The second region is not part of the answer. And then finally, my last region. So my solution to this inequality would be everywhere from -infinity up to -5, or from -2 to infinity. That's where any of those numbers in those regions will be a solution to this. We'll make it true. Okay, next one. Let's find all of our critical values. Find all your x-intercepts by setting the top equal to 0. Find all your discontinuities by setting the bottom equal to 0, and that is going to have to be factored. That'll be x minus 6 and x plus 1. So that'd be 6 and -1. So there's your 3 critical values. Now remember, even if it were or equal to's, these don't get included. But this one's less than, so everything's an open circle. Open circle at 0, open circle at 6, and an open circle at -1. So we're going to test values in each region. Let's find us some test values, maybe -4. Now this one, it's always bad when it's a small interval like that. So we're going to have to make up a fraction like -1/2. We'll test 2 and we'll test 8. So let's plug those values into our original function and let's see what happens. And here's the results I got. -2/5 is less than 0 and -1/6 is less than 0. So therefore that's my only solution. So everywhere in the interval where -4 is located is a solution, and everywhere where the interval where 2 is a solution. So my solution is going to be all values from -infinity up to -1, open circle, union everywhere from 0 up to 6. So there's all my solution region. Number 3. Set the top equal to 0, set the bottom equal to 0. When you're setting the top equal to 0, again, that tells you your x-intercepts, and that's going to be x equals +3 and -3 are going to be your solutions there. And let's go ahead and do this. Your x-intercepts get closed circles. So at -3 and at +3, you get a closed circle. Then you set the bottom equal to 0. That's all your holes and asymptote lines. You have an asymptote line here at a -4. Those get open circles. You cannot include an asymptote line. You then select values from each region. We'll do -6. Here we're going to have to do -3.5. We can do a 0 very easy and maybe a 4. So let's test those out and see which ones work. And here are the results for my test. The only true statements are 6.5 is greater than 0 and 7/8 is greater than 0. So that's going to be this small region right here, or the region, let's see, the other solution was 7 when I plugged 4 in. So therefore that would be this region. And notice that most of the time, now this is not always the case, but most of the time, every other region. Once you find one, it's normally every other region that works. So do not include -4 because it was an asymptote line, up to -3, which is included because of the or equal, or your solution is all values from +3 to infinity, and we never include infinity. That's it. Number 4, set the top equal to 0, and that tells you your zeros, and you have 1 at 6. And we can do, since it's or equal to, we can go ahead and do a solid circle at 6. Now let's find any possible holes or asymptote lines by setting the bottom equal to 0. Let's factor it. You get x plus 3 times x plus 7. So your asymptote lines are located at -3 and at -7, and those will be, again, open circles. Let's test, find test points. We'll test -8, -4, 0, and 8. Let's plug those in and see what happens. And again, here are my results for my test. And again, the main thing that you're concerned with as you're plugging this in, and you might even miss the numbers sometimes as you plug them in, as long as you're close, honestly, it really don't matter because you're only concerned with, is it positive or negative? Because positive values will be above, negative values will be below. So is this stuff, when I plug it in, positive or negative? Because if it's negative, it's true, like here. This is true because negative 14/5 is less than 0, and negative 2/7 is less than 0. So my true statements come from this region and this region. So my answer is all values from negative infinity up to this value of, I believe it was negative 7, not including negative 7 because it was an asymptote line, or all values from negative 3 to 6. And we can't include 6 because that was a 0. The next one, number 5. Let's go ahead and set the top equal to 0. To find, again, we're finding critical values. This will give me all my x-intercepts. So factor, that's going to be an x minus 4 and an x minus 1. So you have x-intercepts at 4 and 1. Set the bottom equal to 0. Let's go ahead and factor it as we write it down. That's x times x plus 2. When you set it equal to 0, it'll give you all your wholes or vertical asymptotes, and it's located at 0 and at negative 2. This is less than or equal to. So let's go ahead and put solid circles at our x-intercepts, which were located at 4 and 1. And let's put an open circle at our wholes, which are, at our vertical asymptotes, which is negative 2 and 0. Choose some test regions, or test points. We'll test negative 4, negative 1, which right here. Here we're going to have to test a fraction like 1/2, and then maybe we'll test positive 2 and positive 6. Plugging those values in, here's what we're going to get. Okay, now let's check and see their true statements. Negative 10 is less than 0, and negative 1/4 is less than 0. So that's the only two true statements. So that would be every interval where negative 1 is located, which is this interval, and the interval where 2 is located, which is this interval. That's your solutions. So open circle at negative 2, that's an asymptote line. So negative 2 up to 0, which was also an asymptote line, or the interval from 1 to 4 will be your solution intervals. So if I were to ask you, is the number 3 a solution to this inequality? You would tell me yes, because the number 3 is located in this interval. So once you have this solution inequality, you know every value that's going to be a solution. Number 6, set the top equal to 0, and let's find our x-intercepts. I'm going to go ahead and factor that as I write it down to save ourselves a step. X and x, positive 7 and a negative 2. So that gives you x-intercepts at negative 7 and at positive 2. Set the bottom equal to 0, and that will tell you your wholes or vertical asymptotes. X and x, a positive 8 and a negative 5. I believe that's right. So you will have a vertical asymptote at negative 8 and at positive 5. So therefore, since it's or just greater than, we don't have to worry about closed circles at all. So we have an open circle at negative 7. We have an open circle at 2. We have an open circle at 5. And we have an open circle at negative 8. So let's choose some test values. To the left negative 8 over here, we'll try negative 9. We're going to try in between negative 7 and negative 8 be negative 7.5. 0 is always easy to plug in. Let me circle it down here. The number 4 and the number 6. And so let's plug those in and see what happens. Okay, here's our conclusion. Negative 9 is a solution because 11/7 is positive. 0 is a solution because 7/20 is positive, and 6 is a solution because 26/7 is a positive. So therefore, my solutions are where negative 9 is. So over here, where 0 is, which is this region, and where 6 is, which is this region to infinity. So my solutions are all values from negative infinity up to negative 8, or all values from negative 7 up to 2, or all values from 5 to infinity. Now, one mistake that people do like to make here, so be careful with it, when you're finding these regions, when you're seeing which ones are the right regions, do not use your test values. Okay, 0 is a point in this region that we use to test, but actually use the zeros and the asymptote lines when you're actually naming the regions. Okay, number 7, we have a problem to begin with because we've always had greater than 0 or less than 0. So step number 1, you've got to move that 1 over. So we now have x minus 7 over 2x minus 2, which actually needs to be factored, 2 parentheses x minus 1 is greater than 0. So the first thing you have to do is let's clean this up. Let's combine this into a single fraction. And the way that we're going to do that, we're going to multiply top and bottom by a common denominator. And it's pretty simple what that common denominator is going to be. And I'm going to go ahead and distribute that on top because I don't have to combine it. So now your common denominator is 2 parentheses x minus 1. Now be cautious again. Here's where people miss this. This minus goes with the whole top. So you have to distribute that out amongst the top. That'll be a negative 2x and a positive 2. So now that cleans up. X minus 2x is a negative 1x. Negative 7 and 2 is a negative 5. And on bottom you have 2 parentheses x minus 1. And now you have what we had on the other problems. It's greater than 0. So next step, let's find all of our x-intercepts. To find the x-intercepts, we set the top equal to 0. You can simply move the x over and you get x is negative 5. So there's your x-intercept, and that's going to be, since it's just greater than, it's going to be an open circle anyway. So at negative 5, we have an open circle. Then we find our asymptote lines and holes by setting the bottom equal to 0. So you have 2 parentheses x minus 1 equals 0. So that's going to be a value of 1. Will be a vertical asymptote, or a hole. Actually be a vertical asymptote for sure there because it's not a factor of the top. So therefore that's your region. So this will be a pretty easy one because you only have 3 regions. Let's test negative 6, let's test 0, and let's test 2. Again, 0 is always a really easy one to test no matter where it's located. Always try to plug that 0 in. So we're going to take those 3 numbers, going to plug them into our original. I would do it to the original values if you'd like to. You could actually plug it into this, or you can plug it into the original, either way. And here's what you're going to get. So here's the conclusion. I actually went with plugging into this afterthought because then you can just deal with positive or negative. And the only solution is going to be right here. 5/2 is greater than 0. So your solution region is where 0 is located. So that's going to be all values from negative 5 up to 1. Okay, our last problem. And you have the same issue here. You have not greater than or less than 0, but you have an actual value over there. So 9 over x minus 4, we do have to move that over. Put the bottom in parentheses. Minus 8 over x minus 3 is less than or equal to 0. So you got to move it over. You have to have the 0 on the right side. And the reason I put those bottoms in parentheses is just because I like for you to see that that is one item. That is an entire binomial. So when you go to find these common denominators, you're going to multiply top and bottom by x minus 3 here. And you're going to multiply top and bottom by x minus 4 over here. So now your common denominator is an x minus 4 times an x minus 3. On top you have 9 parentheses x minus 3, which is 9x minus 27. And here, do not forget to distribute the negative with the 8. That'll be a negative 8x plus 32, and that is less than or equal to 0. Combine your like terms, gives you 1x plus 5 over x minus 4 times x minus 3 is less than or equal to 0. Now you solve it just like the other ones. Critical value, set the top equal to 0. That's going to give you your x-intercepts. So you're going to have an x-intercept at negative 5. And since you are less than or equal to, we're going to shade in, and we're actually going to fill in negative 5. The bottom's equal to 0 anywhere you have a vertical asymptote. So that's going to be at 3 or at 4. And we're going to do open circles there and there. So that's going to be what your graph looks like. So now let's actually find some test values. We're going to test negative 6. Always going to test 0. Here we're going to have to test 3.5. And we are going to test maybe the number 5. So let's plug those in and see what we get. So here's what I get. Negative 6, when I plug it in, gives me negative 1/45 is less than 0. So we're looking for all the negatives. And also 3.5 gives me negative 34 is less than or equal to 0. That's your solutions. So this region that contains negative 6 and the region that contains 3.5, which is that really small region right there. So my solution to this inequality, rational inequality, is negative infinity up to negative 5. And again, I nearly did it. I nearly did that instead of the negative 5. Make sure it's up to the solid or open circle, or the region that goes from 3 up to 4. And again, neither one of those are included because those are asymptote lines. So that's going to be your solutions.